Hi, my name is Gerhard and I'm a data scientist at SAS and a lecturer at business schools and universities. The communication of analytical results and the interpretation of machine learning models is a very important topic for us in data science. We want to make sure that our models are well understood by the business user. This webinar is going to show you 5 tips and tricks how you can better communicate and interpret your models, and which makes your life as data scientist easier. Why are we interested to communicate our results? We want to make sure that the results that we create for the business user are accepted and are well understood. Because if models are well understood, they can be better used in the business process. And this is what we finally want. We want to see our models being used in production and generate benefit for our organization. We also want to avoid last-minute misunderstandings. It very often happens that some information is only implicitly communicated, and only when the model is used in production it turns out that business users understood it in a different way as we did. So when we take a look at the SAS decisioning process, which has the model building part on the left, the model management part in the middle, and the decisioning part on the right, when we speak about communication and interpretation of machine learning models, we know that we move from modeling to the area where our models are used for decisioning process, where they generate decisions and where they generate actions for the operational business. So we want to make sure that the models that we create here generate the accepted benefit here on the right side in the decisioning process. In my webinar, I'm going to present 5 tips and tricks how you can better interpret your machine learning models. We take a look at a way how you can perform interactive cutoff analysis. We also take a look on how you can use a decision tree to explain your complex machine learning models. We take a look on interpretability charts, which you can automatically turn on. We also speak about ideas on how you can quantify the importance of certain explanatory variables. And I show you a coding tip how you can better display the hidden coefficient in regression analysis. If you want to have access to more content, I'm happy if you watch additional videos on the SAS YouTube channel, if you follow me on LinkedIn or Twitter, or if you access content on my GitHub page or take a look on my SAS Pressbooks. When we create predictive models, we want to illustrate to our business users the effect of different cutoff points on the model decisions, and we also want to illustrate the outcome of our predictive model, what does it create and what can be used in the operational process. The way how you can do this is shown in tip number 1. A predictive model generates predictions. For us as a data scientist, this is often very clear. However, we want to illustrate this to our business users and explain them what the output of predictive models are, for example, in a binary classification task of customers responding or not responding to a campaign, that in that case the probability is the fact that the yes event, the response event, takes place. And we want to show and illustrate this to our customers. We also want to show to our customers what different cutoff point decisions affect for the yes or no decision and the proportion of the correct or incorrectly classified customers. If you create, for example, a predictive model with SAS Visual Analytics, you receive the following output. You see which variables are used in the analysis, and you also receive some output on the model quality and other model features. If you click on the icon on the upper right side, you can easily say, I would like to derive the predicted values of this model and store them in a separate variable for further analysis. If you do so, you receive the question how you would like to name your output variables. You have to provide a name for the predicted variable, meaning what is the yes-no event? Is it classified into the yes or into the no category? And you have to provide a name for the variable that holds the probabilities which are predicted for each analysis subject in your data based on the model that you just created. So consequently, you receive new variables in the data as you see it here. In our first step, we take a look of what we can, of what we should do in order to illustrate the predicted probability, as we have it here. It is very important for the business user to see the distribution, to get an understanding that the predictive model that we just generated assigns a probability between 0 and 1 to each analysis subject, saying that, for example, the customers who have a very high response probability are centered here, and the customers who have a very low response probability are centered here. And the decision whether to include them in a campaign now depends on the cutoff point, which they can set at a certain point in order to say those above the cutoff point are responders and those below the cutoff point are non-responders. Such an analysis also allows you to interactively play with the cutoff point now. This is important to illustrate it as an outcome of the predictive model, because this is where the business users base their decisions for marketing actions, for the assignment of fraud investigators, or for credit scoring activities on. And this also means that the consequences of assigning a certain cutoff point affect how many customers are flagged with a yes or with a no flag, what is the expected proportion of false positives, false negatives. This is a very easy part which you can generate based on the variables predicted fraud event. This is where the prediction yes-no event is based on, which we generated early on, and an additional variable which we have here, which is used for the slider bar to dynamically assign the yes-no event. So in our VA report, we just simply drag and drop bar charts where we use on the categorical axis, we use the event whether someone is assigned as a fraud person or to be non-fraudulent based on the selected cutoff. And we also add the information which we have in our training data, whether sometimes in reality was flagged with a fraud, here in orange, or not, here in green. I have shown this here in absolute values and also in relative values. If business now decides for a very strict cutoff point, saying, for example, 26.7%, when you move the slider here, you see that we assign 78 people to the group fraud classified as 1, and a very large group, more than 70,000, to the group fraud classified no. In the relative chart, we see that in this case, we are correct in almost 50% of the cases where we assign someone as a fraudulent person who really had some fraudulent behavior in the past. However, as we are very strict with our cutoff point, we only have 78 customers in total there. If we now move the slider to a lower value, when we are not that strict, we get more people into our group of potential and fraudulent people. So we move up from 78 to 1,400. So the number of people we would like to investigate increases. However, the relative proportion of those who are true fraudulent people in this group decreases as a consequence, as we want to get more, as we are more liberal with our cutoff point. And finally, we see what happens if we move the slider for the cutoff point to a very low value. We get a larger number of observations classified into the yes category. However, our relative correct prediction goes further down. So the ability to play around with the slider here is a very important tool for us as a data scientist in order to illustrate the business user what does it mean to use certain cutoff points in a business decision, and what are the expected consequences on the outcome when the model is being used in production. So with tip number 1, you have seen how easy and how powerful it is to perform interactive analysis for the cutoff point to illustrate the outcome of such decisions on the number of customers classified into the good or into the bad category. And we've also seen how important it is to visualize the distribution of the predicted values to business in order to make them understand what their decision causes and how this looks like from a data point of view. When we create predictive models and business is going to base their business decisions on our predictive model, business often wants to understand how a certain decision has been created and what the reasons for the assignment of a high or of a low predictive value for a certain customers are. For models like decision trees or regression analysis, this is very often straightforward to do, as the decision tree shows its rules and the regression analysis shows which variables have been used with which regression coefficient in the final model. For more complex models like neural networks, gradient boosting, random forest, for example, this is not so easy to achieve. In my tip number 2, I'm presenting a very simple way how you can use a decision tree as a surrogate model to explain why customers received a high or a low predicted probability. Let's assume we build a model based on a gradient boosting. And this model is a very precise model and we would like to use it in production. However, business would still like to understand why some customers receive a high value and some customers receive a low value. Let's take a look how this can be easily done by using a decision tree here. You base the decision tree on the variable, the predicted event probability from your complex machine learning model. So in our case, we generated a gradient boosting model, and this gradient boosting model provides predictions for each customers in the training data. And we are now going to create a decision tree where we would like to explain the response of this predicted probability based on other variables like age, gender, region, promotion time, and other variables to have a meaningful interpretative model for business to see why some customers receive a higher probability, why some customers receive a lower probability. The output of the decision tree is the creation of segments with a predicted high or low probability. So we see here those who have a dark green color are segments which have a higher probability. Other areas like this one have a lower predicted probability. So the predictions are still generated with the very precise gradient boosting model. However, our explanation are based on our surrogate model on our decision tree. And this is now very powerful in order to illustrate the output for business people, for example, for marketing. We can take a look how we can interpret these segments. For example, we see here on the left-hand side a segment like this one. So we can say here in this leaf of the tree we have ladies which are young and which are quite affluent. So this might be the young affluent ladies segment, and this allows business now to define a marketing campaign which is more attractive for this individual target group. We might have other groups like like men who are not that affluent. They only have a predicted probability of 20%. So they are typically in our data group which do not have such a high probability to respond compared to the young affluent ladies, as we saw before, who have a probability of responding with 93%. So we see that the creation of decision trees in order to interpret your machine learning models and use them as a surrogate to explain the content of the model is very easy to achieve and is very powerful for the interpretation and for the communication of the results for further business decisions. We often use machine learning models for predictive analytics that do not directly reveal their logic and the reason why they assign a high or a low value to a certain analysis subject. In tip number 2, we already saw an idea on how to use a decision tree to explain the assignment of high or low values per analysis subject. In this tip, we see typical model interpretability charts and how easily they can be created with SAS Model Studio. The partial dependency plot is one type of model interpretability charts that give you insight in the relationships of input variables on the outcome of your predictive model. You see here a plot with the values of a certain input variable, in this case horsepower, and the relationship to the predicted values on the vertical axis. The values that are shown here by the line chart are, however, not the univariate relationship, but the outcome of the predictive model. What is the effect of variable horsepower together with all other variables on the predictive value of the model? This allows you to study in more detail what is the effect of a certain variable when it's being used in a multivariate model together with other variables. The nice thing with SAS Model Studio is that you can create these models, model interpretability charts automatically by just ticking a box, instead of having to create a complex macro which iterates over many possible values of the other variables in order to get the correct predictions. Another way to interpret your predictive models in a better way is the individual conditional expectation plot, ICE plot. Here you see what is the effect of an individual observation or a cluster of individual observations for a certain variable on the outcome. You can use this to study why for a certain analysis subject or for a group of analysis subject a certain high or low predictive value has been generated. Again, you simply click the checkbox to generate such plots and you receive them automatically in your Model Studio output. The local interpretable model agnostic explanation plots is also a very powerful tool to get a deep insight into your machine learning model and find out which values and which value combinations, or in in a more abstract definition, which regions of your data have a certain effect or have a high importance, why a certain predictive value has been assigned. We see this here in an example of image classification for a frog, and we learn from the line chart that certain regions have a very high effect in order to classify whether this is a frog or not. So we learn which sections in the input data have a very strong relationship on the outcome. And for example, in image mining, this could be, is the predictive model for image classification really able to differentiate a wolf from a husky? Or is it just a background where we see grass or snow and the model just learns in which environment the animal has been pictured and doesn't learn the feature of the animal itself? This is a very powerful application of the so-called line charts for model interpretation. And again, you can just have to click them on by clicking a box. Another powerful way to explain your machine learning models is to use the Shapley additive explanations. Based on the research of Shapley in game theory, this method assigns contributions for each variable in the predictive model. The method is based on the theory, on the research where the assignment of the payout in a game to various players should correspond to the contribution of each player to the total payout. This is now transferred to machine learning, where each variable takes over the role as the player, and the contribution of each variable on the predicted value is considered as the payout and is displayed in graphs like we see it here, and where we can find out that some variables have a higher contribution and other variables have a lower contribution. This tip has shown you how you can use standard interpretability methods like the partial dependency, the line chart, the Shapley explainer on your predictive models, and how easy it is to receive and to turn them on in SAS Model Studio. In our next tip, we want to take a look on how we can quantify the importance of variables. Very often we only discuss the fact that a certain variable is important and others are less important. However, here we want to go one step further and say, what is the effect in terms of euros or dollars on the outcome? Let's take a look at the predictive model, in that case a gradient boosting model, where we see that certain variables have a certain importance in the model. If we now have to make the decision that maybe the variable affluence is not available anymore because maybe it is too expensive to prepare it on a regular basis, maybe the variable has been acquired from an external data provider and we do not extend the contract with this company. We just want to find out what does it mean if a certain variable does no longer exist. We see here that the variable is the second most important variable. However, if we remove it, what will happen next? Will other variables substitute the missing content, the missing effect of this variable, and therefore compensate the predictive power and the story of the variables in the model? Or will the model quality go down? As we saw, it's a very important variable and it decreases the predictive power if it's not available. In order to find this out, the step is very simple. You create a copy of your model, as you see it here, and as a next step, you simply remove the variable that we want to find out whether it's important or not. And then we train a new model on the existing dataset and compare the old to the new model. When we compare the old and the new model, as we see it here in the lift chart, we find out that the lift drops from 3.47 to 307. This means that our affluence variable had some predictive power, which could not be compensated by the other variables. The model quality goes down. However, in order to find out now what does it mean in terms of euros or dollars, we need to prepare a certain calculation based on our predictive modeling output. It is very simple to calculate such a business case. Let's do the following simple calculation together. Assume we have 2 million of customers in our customer database. Usually a campaign offer or a campaign initiative is sent to the top 5% of those with the highest response score, which means that the campaign offer is sent to 100,000 customers. If a customer responds and buys something or subscribes for services at our company, we calculate with an average profit of 35 euros. If we now want to find out what does this mean for the old and the new model, we also have to know what is the autonomous, the baseline response, if we wouldn't apply any analytics. So for example, if on average 12% of the customers respond anyhow, if we do not prioritize them by selecting from a predictive model, we can now see that 12% as a baseline multiplied by the lift of the better model 3.47 means that we have a response rate of 41.6 and with the other model of 36.8. So we see that the difference between these two models is a difference of 4.8% in response rate, and meaning that of those customers which we are talking to in the top 5%, we miss 4.8 of responders. If we now calculate what this means in terms of euros, we do this simple following calculation. Not having the affluence variable costs us 4.8% of response in our target group, meaning 100,000 customers times 4.8% means that we miss 4,800 responders. For each responder we have 35 euros on average, so we see that not having the affluence variable costs us per campaign approximately 168,000 euros. This is a very simple calculation and a simple analysis which we can run here in order to quantify on average what this means in terms of effect if certain variables are not in place. Please consider that here it is not necessarily to have the most accurate results. Of course, the more time you invest and the more precise you are, the more precise your result will be. However, very often it's important to have just a rough calculation to find out what on average does it mean having a certain variable or not. And it's for us important to find out rather, is this something around 160,000 or is it rather 16,000 or is it rather 1.6 million? And such calculations help you to qualify this in a certain range. And be aware that you also should perform such calculations even if you cannot precisely estimate all these numbers and just have rough estimates of values like what is the average response rate, what is the number of the baseline response. Still go ahead and run such analysis. In my SAS Press book, Data Quality for Analytics Using SAS, I have performed a large number of such simulations. What does it mean if a certain variable is not available? What does it mean if the number of missing values increases? What does it mean if the number of random errors in the data increases? So you can find there an illustration on a business case study in euro and then in dollar values. What does it mean if certain things happen to your data? How does model quality go down? You can download a couple of examples on GitHub for that, and I plan for a future video series like this in a webinar to present more details on that. The same calculation as we now performed for the variable effluence to find out what is the expected drop in accuracy if we have the variable or if we do not have it, can also be performed in order to compare certain models. Let's take a look at the following lift chart. We see here we have three models: a decision tree, a logistic regression, and a gradient boosting. And we see that the gradient boosting has the best performance, the logistic regression second best, and the decision tree is going on place number 3 when we compare the lift value at the top 5%. And we can now calculate in the same way as we did before, what does it mean to, for example, not use the gradient boosting model because we want to use a regression model which is easier to interpret. We see that out of this calculation it comes out 63,000 per campaign are we losing because we want to have the interpretable logistic regression and we are not using the gradient boosting model. This is very often very helpful in conversations with your business users and internally, whether you should use a more complex model or not. And very often it's important for you to be able to highlight what does it mean if you use a certain model or not. And you can calculate also the same, what does it mean to not use the logistic regression but a decision tree. These calculations can be very easily created and performed. This tip has shown us how simple it is with some basic calculations to quantify the importance of a certain variable or the importance of a certain modeling type in euros or in dollars compared to just communicating the lift, the ROC value, or any other model assessment measure. It's very easy to apply this, and I highly recommend to perform such calculations when you speak to your business colleagues who apply your analytical models. When we use regression analysis for predictive modeling, we very often encounter the situation when we communicate our results to the business user that the interpretation of categorical variables and especially of the reference category is a very tricky one. The tip number 5 shows an idea on how you can calculate the regression coefficient for the hidden value for the reference category in order to have a better interpretation for your business users. The example that I'm using here is a survival analysis example where I use data from employee headcount analysis of a company to compare the careers per employee on what might be the effects that some of them have quite a long career and are still in the data at the end of our observation periods, and others have quite short careers. This is a case study which I presented in my Applying Data Science case studies book, and I plan to run a webinar on deeper analysis with this data here as part of this webinar series. Today we only take a look on how we can analyze this data in regression analysis. So for example, there might be the question, how long will a certain employee stay with our company? So this means, given certain risk factors like department, gender, or whether he has technical know-how or not, what is the expected survival at a certain point in time, or what is the probability to resign within a certain period, in that case 6 months. In order to do this, we need to use a proportional hazard regression model, as our data do not have a fixed endpoint, but some of them are censored. So in order to model this, we use the phreg procedure, which is part of SAS DAT, and define our regression model where we analyze the duration, so the length of the career. We also consider the status. Has he left the company or is he still with the company? And use certain variables like department, gender, techno-how as input variables. As these are categorical variables, we need to define them as a class variable in order to tell the procedure that these variables have content which is not an interval variable but a categorical variable. Here we use the reference coding. Reference coding meaning that one category, in that case the administration department, is used as the reference category, and all the other coefficients are interpreted as a difference between marketing and administration department, between the sales engineer and the administration department, and so on. When we now run the analysis, we see that we only receive the coefficients for those set of categories because they are interpreted marketing compared to administration, sales engineer compared to administration, and so on. This, however, is not always easy to communicate to business people. Why does a certain category has to be selected as the baseline category? Which should we use? Why is the value for that 0? And I would like to introduce you a method which I found very useful in my projects at customer sites, how I could better communicate the content for the customer. So we see here, so when we compare the effect coding and the reference coding, we see what we just did in the reference coding, that we have the reference coding and the administration class with 0 and our parameter estimates. In contrary, if we go and use the effect coding and not the reference coding, this means that for the selected reference category, here again it is administration, not values of 0 are used, but values of -1 are used. This means that now the interpretation of the other coefficients is different compared to in reference coding. Let's take a look how this looks. On the left-hand side, you see the coefficients of the parameter estimates, and we see the sales engineers have the highest coefficient, then the sales representatives, which we also see here in our data. If we want to find out what is the value for administration, we know it is 0 because we selected it as the reference category in reference coding. If we now want to find out what does this mean for the effect coding, we see that this value is -6.4 and lies something here. We see that this is just a shift compared to the reference coding. However, it now can be easier and better interpreted also by business people, because none of the classes has in the interpretation been explicitly selected as the 0 value. So we can say marketing and administration have, compared to the average, a better performance. They have a lower risk to cancel. Those have a little bit higher risk on average to cancel and can be much easier interpreted what the effect of a certain variable is in the respective model. In order to calculate this value of -645, there's an easy way to do so. If we have, for example, the model that we just created with the effect coding, and the output is the following, we see we have the parameters of all the regression output lists the parameters of all other coefficients compared to the reference category. We see that we here have now a way that we just sum up these values, we change the sign of the calculation, and we receive -654. So it's very easy to calculate this missing or this hidden coefficient for the reference category just by simple calculation, adding up the other coefficients of the categories, changing the sign, and we receive this value. In order to automate this calculation, I have generated a simple macro in SAS, which is the calc reference category macro, and this helps you to automatically calculate the hidden regression coefficient for the reference category for all your class variables. You can download this macro on my GitHub page, and you can easily apply this to the output of your SAS regression procedures to receive the output for that. In parallel, I'm also preparing a contribution on SAS communities where you can read an article for the application of the macro and for the business case of that, and I will also add this to the appendix of this webinar series. So what we've seen here is that in regression analysis, in order to better communicate the results for the business department, it's very good often not to use the reference encoding but the effect encoding, and it's very simple to calculate the value of the hidden regression coefficient for the reference category. In this webinar series, I've presented a collection of tips and tricks on how you can better interpret your analytical results and communicate your machine learning models. The conclusion is that communicating model results has many dimensions. It is not just one method or one graph or one interpretation chart. It has, depending on the needs of your business user, a different flavor depending on your organization and your respective business problem. Also be aware that SAS offers you a broad range of tools that help you to illustrate your findings and provide methods to show your business users the outcome of your analytical models. And we are interested to do so because we know that machine learning models which we create, which are understood, are likely to have a higher business impact because our business users understand it better. The probability that the model can be applied in production is higher, and this is finally what makes us as a data scientist happy. I hope you enjoyed my session. I look forward to seeing you at the next webinar series soon. So when we take a look at the SAS decisioning process, which has the model building part on the left, the model management part in the middle, and the decisioning part on the right, when we speak about communication and interpretation of machine learning models, we know that we move from modeling to the area where our models are used for decisioning process, where they generate decisions and where they generate actions for the operational business. So we want to make sure that the models that we create here generate the accepted benefit here on the right side in the decisioning process. If you have any comments or questions, I'm happy if you post them to the thread below this webinar, or you contact me on any of my social media channels, and I'm happy to answer your questions and receive your comments. Thank you very much.